constructor for SS, to the application of the constructor, the SS constructor, to the even zero constructor, right? This is very much just a piece of data. It's a sequence of applications of the constructors of this data, which we can interpret as a proof, but we could also interpret as data. I mean, there is no difference here. And indeed, if we wanted to, we don't have to use tactics at all to build the proof of this theorem, right? We could actually manually, we can check the type of this expression that we got out. Interestingly, well, maybe not interestingly, this expression that we built up has precisely the type, the statement of the original theorem, right? There's no distinction. And well, on top of this, we can actually directly build proof objects inside the script itself, right? So instead of calling tactics, we can say apply, and we manually provided this definition that we built up by hand. And because this has exactly, this is a witness or a proof of the exact goal we're trying to prove, EV4, you can see up here, it just solves the goal immediately. So we're handing, instead of interactively building up this proof script using tactics, we're just telling coq exactly what to do. Like here's the concrete proof object.
So
yeah?
This is possible only for actively defined position, or like a proof object?
Nope. You can actually, so I think we're going to get into this, but you can manually construct an expression corresponding to the proof term for any provable proposition in coq. And because this is precisely what happens under the hood when you're using tactics. Okay. And in fact, it's sort of cool to, when you're walking through the proof of a particular proposition, you can actually ask coq to show you what the intermediate sort of proof term you're building up looks like using this command show proof. And in fact, I encourage you to do that for some of the simple examples. So let me switch over to this proof objects buffer. It's really instructive to see this in action. So, okay. Okay, so did it just it? Okay.
Raise it up a little.
Yeah. Okay, so when we start out, what is the proof object we've built up? We don't, hopefully this is readable. We have this question mark goal. So this says there is some hole, we need to fill it in completely. We haven't constructed any underlying object, okay? So we haven't done anything. But after we apply this tactic, or after we apply this proof rule, what do we have now? Well, now we see under the hood what we've built up is a partial proof object, right? It's the application of this constructor to some subterm, some sub-goal, right? And intuitively, the type of this hole, right, is exactly the proposition we're trying to prove up right up there, right? So think about it. If I want to prove that 4 is even, what do I need to prove? I need to prove that 2 is even. So I need a proof object exhibiting that fact. That is the type that is our goal up here. And it's also the type of this hole, of this explicit proof term we're building up. So as we walk through this proof, we apply the next one. And of course, we have application of this constructor twice. And then we can apply the constructor that, for showing that 0 is even. And if we show the proof, well, now that there are no more sub-goals, this means there are no more holes in the underlying term that we need to fill in, right? So we've completely finished the proof. And in fact, when you hit QED, what happened, all coq is doing is it takes this proof term that you've built up with no more holes in it, it does a quick final type checking step, and then it assigns that definition to this identifier that you defined the theorem with, that you were using for the theorem. Yeah?
Sometimes with these proofs, there's more than one way to get to prove it.
Yep.
And so if I did a different proof to get the conclusion, and I said, show me that, print that proof object, would I see the?
It would be different. It would be different. Yeah. So if you can imagine, if we had EVSS prime, which had the exact same, the constructor had the exact same assumptions as EVSS. It just had a different thing. If we applied that, then in the underlying proof term, when we applied that constructor, that is the constructor you would see in the proof term.
So this is,
right?
you know, like the idea where you say intuitionistic sort of thinking.
Yes.
A proposition is identified with a set of its proofs. And so all of these proof objects we build up are sort of inhabitants of the type
yes.
of the proposition, which
yes.
is the theorem that we've proven.
That is exactly,
that in turn belongs
yep.
to the prop.
That is exactly right. Cool. That is exactly right. So the question was, well, the question was, you know, in this Curry-Howard isomorphism interpretation, all the possible proofs or proof objects of a particular proposition precisely correspond to the different ways we can construct evidence of that proof. So everything that has a certain type corresponds to a proof of that type. And that is precisely the intuition or the correspondence we're exploiting in coq here. Okay, so it's worth noting that these tactic proofs are a way of interactively building up these rather complex terms and expressions, right? When we're calling tactics, we're doing rewriting. The underlying proof terms can actually get a little ugly to the point where it might be cumbersome to build them up by hand. So it's making it more convenient to build up these objects, but it's not necessary. You could, as I said before, just write down everything manually, explicitly write out the proof term. As long as it has the type of the proposition that you're trying to prove, you're golden. Right? So for this rather simple EV underscore proving that 4 is even, we can just use definition instead of theorem and just give it the proof term directly. And this is fine. This is, morally speaking, this is the exact same thing as our first interactive proof, our second interactive proof, where we used apply, our third interactive proof, where I can't remember what we did, and then this final one where we just used a definition. These are all the same proof term under the hood. The only difference is how we constructed them, using tactics or giving the manual evidence. Yeah?
So what would be the proof object for an axiom or an admitted proof?
So you're saying, what would the proof object be for an axiom? The answer to that is that an axiom has no admitted proof object. If you can imagine, it asserts it effectively asserts there is some proof object with this type, but it doesn't say what that is. So that constant sort of represents the proof object, but it's not. It's abstract. It's just an identifier with of that type. Yeah.
In your current proof state, you can form a term of type T. How can you just assign that to a new variable?
If you
Like definition. Like I know how to do it at the top level, but how can you do that?
Oh. So you're asking, can you define new constants inside a proof script? This is actually a bad proof taste in the sense that you probably should not do it inside a proof script because, in fact, I'm not even. Let me see. I don't think you can. And here's the issue. So when you're working inside a proof script, right, you could imagine writing a definition that might depend on some variables in the context, right, some assumptions that you have. And outside of that particular proof script, that definition, those terms aren't in scope. So if you could define a definition that way, it might allow some terms to escape because those might be open if you refer to that definition outside the proof you're working on. So generally speaking, if you want to define a new object or expression, you should do it outside of the proof script. Every sort of proof script should be self-contained. And there are a couple of notable exceptions, but I don't know if that is a satisfying answer, but yeah.
Sure.
Yep.
So the Curry-Howard correspondence is giving us this correspondence between propositions and types.
Yeah.
Yet coq is explicitly distinguishing between the two by having type and coq.
Right.
Give us kind of situation why that's a good idea.
Right. So the question was, okay, if props and types are the same thing, and that's what I keep saying over and over, why do we bother distinguishing between a prop and a type at all, right? If they're equivalent, why do we make this distinction in coq? And the answer to that question is has to do with an idea that's come up a couple of times in reference to extraction. So we actually build up these Galena programs, and we might actually want to extract them to OCaml or equivalent functional programs. And morally speaking, the idea is that when we say something has type prop, we're saying these have no computational relevance, and when you do extraction, you can just throw these terms away, right? Because they're not useful when you're actually computing the functions. So morally speaking, it's you could think of it as only being there as an identifier that these are just to be interpreted as proofs and can be discarded freely. I think.
So the types are extracted, and the props are not.
Yes, or set. That's exactly right. Yeah.
So if I write a proof of a theorem, and if you write a proof of the same theorem, will our proof objects match?
It depends. So the question is, if I write a proof of a theorem and you write a proof of a theorem, will our proof objects match? The answer is, it depends. Like if we built it in the same way, right?
So effectively, be constructing two terms of the same type.
Yes.
Terms of the same type.
Well, think about it this way. If I'm struggling to come up with a non-trivial example. Suppose that you asked me to write a plus function, and you wrote a plus function. We might write different functions, right? But they're going to have the same type, right? And I might have an error in my plus function because maybe I'm not that good a coder, I don't know. And then they would have different results too. So there's no guarantee just from the type that the term that inhabits it is the same, right? Or maybe here's a better way to say it. If I define foo, it's a magic constant of type nat, I might say it's 0, and you might define it to be 3, right? I don't know. So we could write down different definitions of foo. They're going to have the same type, but concretely, the underlying data that inhabits that type are different. And the same thing can be true for like proofs, right? In fact, there are an infinite number of ways of constructing natural numbers. So it's very unlikely we would have coincided. But sort of the important point here regarding like computational irrelevance is for proofs, we don't care what the proof object is. All we care about is that it exists. And so it's not going to impact, we're not going to do anything with these proofs computationally. We're only going to use them, pass them as assumptions to other proofs. So it doesn't matter how they were constructed, as long as we're choosing to interpret them as propositions. And this is sort of a key difference between, the key moral difference between propositions and types, and why they actually make this distinction between prop and type when you're doing extraction, because you're saying, okay, you don't actually need to compute with these proofs under the hood. Okay, yeah?
So even though coq has types and has propositions, we cannot encode the correspondence within coq, because as you just said, for propositions, we only care about whether they exist or do not exist, whereas in general, types may have multiple inhabitants. And so it's a correspondence and not an isomorphism.
The question was, can we encode the Curry-Howard isomorphism in coq itself? We probably can't because it's a correspondence and not an isomorphism. So there is no direct mapping between types and props. I'm struggling to I'm struggling to interpret this question in a way that I can answer it satisfyingly. Here's what I'll say as an answer. So in coq, you cannot use a prop, something that lives in prop, to build something of type. But you can use something of type to build something of type prop. So, and the reason for that is that props are not computationally relevant. So there's no way of doing there's no way of matching on them in such a way that you could construct a different computationally relevant piece of data. And that is all I want to say about that, I think. We could talk more offline if you want.
But it is called the Curry-Howard isomorphism.
Yeah, so the isomorphism is, or some people call it a correspondence, right? It's just, this is more of a philosophical isomorphism or correspondence. It's like noticing that this connection exists rather than actually asserting some deep, well, I mean, it is sort of a deep mathematical result, but it's a little bit hard to formalize. It's more of a philosophical argument, I would say. Yeah. It truly is a sort of a worldview of looking at choosing to interpret things in two different ways and noticing they can be interpreted. Two things that seem on the surface to be quite different are in fact very related. Let's see some more examples of that. Do we? Okay, we got 20 minutes. 10 minutes. I think what I'd really like to get to is this sort of interesting idea. So it turns out that there is nothing stopping us from building up functions or definitions using tactics. It turns out in much the same way that you could build up this proof object under the hood using tactics, you can actually build up functions using tactics in coq. You can actually use these tactics as powerful metaprogramming assistants to help you build up, say, an add function here. So to see what happens, I think it's worth looking under the hood for this add1 definition. And we're going to print the proof all along the way. Okay, so when we start out, again, we have nothing in hand. What we're trying to do here is we're trying to build an inhabitant of the type nat arrow nat. So this is a function, right? So what does intro do? How do we build up terms of type x arrow y? What is the constructor? Anyone?
Have you used intro before? It seems like we've always been using intros.
You can imagine intros is isomorphic. I mean, intro is just saying, I'm only going to introduce one thing. So, in fact, well, yeah. Okay, so after we intro, what do we have under the hood? Well, we said, okay, what intro does is it says, if I want to build something x arrow y, I can build it up using as a function, right, as a lambda term. So under the hood, I've built up a function, right, and I have a goal. The goal corresponds to this goal state. Now, if you think, this might be a little advanced, but if you think about what's going on here, here we're trying to build up a term with the type nat, but it's inside a function body. So what do we get inside a function body? Well, we have access to all of the arguments of that function, right? So everything above the line, our set of assumptions here, correspond to arguments that are bound by some function type, or by some function lambda term. Okay, so now what can we do? So what is the type of S? It has type nat arrow nat. So we can apply S, right? Another way, yeah. And now under the hood, what do we have? Well, we have a new goal. Again, it has type nat, and we have a nat in scope. But the proof object, or the object term we're constructing under the hood, actually has an S that's sort of partially filled in the hole, and now we have a new goal. And then, of course, we can apply our assumption and hit defined. And now we have this add function that does exactly what we thought it would. It's going to add 1 to its argument. OK, so here's another way of thinking of it. When we see, if we're looking at interpreting, let's say, x arrow y logically, what is one way of thinking of it? It says, if x, then y. Under the Curry-Howard isomorphism, if we choose to think of this as a function, it says this x arrow y, or x implies y, means if you give me some evidence that x holds, I will produce for you evidence that y holds, right? Now, what is nat NAT is a particularly weak proposition in some sense.